Okay, let's get to the C part of this problem. We already saw that the solution for the velocity when it's on the plateau is this velocity. So if you had plugged in your numbers, this would be a number right here. So the last part of the problem, which is C, is how far would the spring be compressed after the roller coaster came in contact with it? So that's that distance here. Okay. So guess what? You could choose this as your initial condition and this is your final. You could choose this as your initial condition and this is your final. It really doesn't matter because the energy is neither created nor destroyed. It only changes from one form to another. So I tell you what, this time, why don't we use, since we just solved for this velocity, let's say that we look at this condition right here as our initial and this is our final. So in its initial condition, it has potential energy where the initial H, in this case it's H initial, is 50 meters. So it has mgh. It's still moving, and it's moving at this velocity that we solved for in part B, but that V prime number is now going to be our V initial. So this becomes 1/2 mv squared, where that V is now this V. And it's not in contact with the spring, so we don't have the last term, so we'll just leave it as this, because this term is now 0. Now, when it gets down here, it lost potential energy, so it must have sped up because it converted that to kinetic energy. So it has no mgh, or h prime in this case, but it does have kinetic energy. Oh, actually, just thought about that. This is not at the instant that it comes in contact with the spring. We're solving for after it compresses. So the spring would have brought the kart to a stop. So in that case, it has no kinetic energy because we're assuming the kart has now come to a complete rest. So when the spring is at its maximum compression, the kart is no longer moving. So it doesn't even have kinetic energy anymore. So now it simply has 1/2 kx prime squared, where x prime is the distance that the spring has been compressed. So now, if you do know the value of k, which I here gave you in this problem, just solve for your unknown, which is x. So you multiply both sides by 2. And divide both sides by k. And take the square root to get rid of the radical, to get rid of the squared. So here would be your final answer, which is the distance that the spring would have been compressed. But remember, this is a specific problem. What were the strategies that you could apply to any potential energy problem or conservation of energy problem? Write the entire conservation of energy on your paper. Why do I want you to write the whole thing? Because then it'll help you memorize and remember what the actual equation is. Then get into the practice of looking at your initial conditions and canceling out the terms that, are 0, so that you simplify the overall equation to be an equation that is specifically for your problem. After you simplify the conservation of energy, then you solve for the unknown value that you want. Then plug in your numbers, and you're ready to get to your final answer. Give the problem a try on your own, and if you get stuck, rewind the video, get a little hint from what the video says, pause it, and try it again and get through the video. Feel free to choose different numbers, try different sets of numbers, try different sets of unknowns, because the process is how to simplify the equation to get the answer that you want.